Cool. All right, well, thanks for coming to my talk today. My name is Karl Sickendick, and we're going to talk about Ghidra, reverse engineering, and PCode emulation. So first we've got a little description of what Ghidra is. Then we're going to talk about PCode emulation and a tool that I built specifically for that. And then we're going to talk about, more generally, how to do Ghidra scripting with the Python programming language. So first of all, though, who am I? Who the heck is this guy in front of you? My name is Karl Sickendick, and if you'd like to follow along, my Twitter handle's up there. I posted a link to a GitHub repo that's got all this information. So feel free to check in there, follow the slides, download the code, whatever you want. My day job is I'm active duty in the Air Force. They've got me stationed up at Idaho National Labs for a year, which is a pretty sweet gig. I'm a fellow, and that means that I talk to the researchers, talk to the Air Force, participate in some research, do whatever seems fun. It's a great gig. But my background is some cyber capability and tactics development. So I'm pretty happy to be here. This is my first year at SAINTCON. It seems awesome so far. Those are some great keynotes this morning, and thanks for showing up to my talk. It's awesome. All right, so who's used Ghidra before? Few. Who is good at Ghidra, or good enough? Okay, awesome, cool. So I'm not like a Ghidra guru or anything, but I've used it at least since it came out. It's pretty great, I think, and it's fun. So we're going to go over first what it is and a little bit of how to use it. So it's an open source tool. It was released by the NSA. It's your tax dollars at work. So other than that, it's free. It's got a lot of great features. The biggest one, in my opinion, is the decompiler. So the way that works, Ghidra's got SLAY modules in it that understand the binary data for a bunch of different architectures. Each SLAY module is for an architecture. A SLAY module can pull that code up into PCode, which is an architecture agnostic intermediate language for Ghidra. And then Ghidra's decompiler understands PCode to pull out program flow and figure out essentially what the C code was that went into this program. So that's a feature in IDA that you get to pay for. And frankly, I'm partial to this one regardless. Excuse me. So how do you set it up? Download it, install OpenJDK 11, unzip Ghidra wherever you want, and go in there and execute Ghidra run or Ghidra run.bat if you're on Windows. It's a Java application, so it works everywhere. Dual monitors is strongly suggested. So if you need a reason for your boss to buy you a second monitor, you can parrot that, and I'm sure the funding will just fly off the shelf. So how is Ghidra organized? Once you open it up, you're going to create a project, and you can create a local or a shared project. So if you create a shared project and you've got a Ghidra server, then your whole team can work together and contribute to the reverse engineering store in this project. So you can add new binaries, you can track even the version of your decompilation as you go along. So if somebody makes a stupid change, you can go and figure out who that was and blame them. It also shares the data structures between all the different users. And there's even some change merging that's built into that Ghidra server, so you don't accidentally stomp on each other's commits. And if you're doing this just by yourself, you don't need a Ghidra server. You just have a local project, a non-shared project, and it works great still. Ghidra also can open some file systems, so you can, if you've got a file system binary, you can pull the binaries on there that you might be interested out right into Ghidra, import them that way. Some of the architectures that are supported are listed here. You get a lot of the typical ones: ARM, x86, 32 and 64-bit. You've also got some weird ones. A bunch of microprocessors are supported, some older architectures. And so again, because there's a SLAY module for each of these architectures, you can disassemble and then you can decompile them using Ghidra. So how does that look? What does that look like? You open up Ghidra, Ghidra run, you create a new project under the file menu, then you import a file under the file menu, and now you're going to be in the state that you see here. You can organize these into folders and such, but then if you double click on that file that you've imported, now you get to the main window. So in the center of the screen, there's the program listing, and this shows the assembly instructions, the data that's all in this file. That's kind of the main window for most people that are used to static analysis. We're going to talk about the other parts of the screen as we go on, but really the first thing that'll pop up when you open a new binary is this analysis window. Before Ghidra can understand where all the functions and the data are, it's got to analyze it. So when you're doing this yourself, you can scroll through and see the massive list of different analyses that you can turn on and off, but just start with the default, hit analyze. It works quite well. Once you've done that, Ghidra will know the list of functions, or at least the ones that it was able to find, and they'll be available in this symbol tree window on the left center of your screen. So you can use that to find the specific functions you're interested in starting your analysis with. On Linux, a great one to start with is main. So here we see a program listing for the main function in a binary. This was a x86 64 binary. At the top, or in the middle of the screen, you'll notice there's no assembly. That's because at the top of each function, the first thing the program list is going to show you is Ghidra's mapping of nice English variable names to stack locations and registers. So if you need that mapping, it's at the top of the function. Just scroll down a little bit and you'll hit the code that you're expecting. So we're looking at the main function prologue here. The first instruction is push RBP. So save off that base pointer before you do the function. How do we see the PCode? This icon is in the top right of the program listing screen. So if you click on it, you'll get this drop down. They'll show all of the different types of data Ghidra can show you in that program listing window about the function that you're on. One of them is PCode. It's the highlighted one. If you right-click on that, if you're on this Instructions and Data tab, there's multiple tabs of potential data. If you're on that tab, you right-click on PCode, you can click Enable, and you'll see now the program listing has got not only the assembly, but also the PCode down to the side of it. Let's look at that a little bit more closely. So push RBP, who gets what that does? Take the base pointer, put it onto the stack. On x64, a lot of us are familiar with x86 programming, so the PCode is not going to come as any surprise to you. The first thing you've got to do is for some reason, it takes that register, it saves off a copy of it in a temporary state space, which is that U2510. That'll never get written to again. That's kind of a cool fact. But it saves off a copy of the base pointer. At the end, you can see it takes that copy and puts it into memory wherever the stack pointer is at that point. But before that, in the middle, it's got to decrement the stack pointer. So it's got to grow the stack pointer down, and then you store RBP at the location on the stack that the stack pointer currently points to. So everybody knew that, a lot of people knew that the RBP got pushed onto the stack, but the exact semantics of how this works in x86, you may or may not remember, especially if you move between different architectures. So in here we've got a different architecture. We've got an ARM64 binary. It's the prologue for that main function, and right here we've got the STP instruction. It's the first instruction in the function. It's probably going to do the same thing as the x64 version. It's probably going to push some state onto the stack, but I don't usually remember what STP does. You can look at the PCode, and you can see pretty quickly exactly what that instruction is doing. You can see, so if you read through this, you can see exactly what the semantics of that instruction are. Another great feature of Ghidra, if you right-click on STP and then click on Processor Manual, it'll either pop up the manual right to that spot, or it'll tell you where to download that manual if that's protected by copyright. So Moving between architectures is quite easy to do on Ghidra. It's easier than a lot of other tools that I've seen. All right, so we've seen the PCode, we've seen the assembly. Let's see the decompilation. That's what we're here for, Karl. On the right side is the decompilation window. And again, Ghidra does this by taking that processor-agnostic PCode and figuring out the code flow. We're going to zoom in on that in a little bit. But now we're going to talk about a couple strategies to improve the decompilation. By default, there's only so much that Ghidra can learn, can figure out about how that C code worked. So you can improve it by right-clicking on the function name in the decompilation and editing the function signature. So here, we knew pretty quickly what the main function was. You can set the name properly. We know the typical way a main function is called. So you can set the data types and the names of each of the parameters. And if you commit that in Ghidra, it's going to propagate that information as far as it can through your code. So it's going to save off the names and the types. It's going to propagate them to other spots. Another way to improve your decompilation is to build and assign data structures wherever they are in the code. So if it's in the data of the binary, you would do that in the program listing. If it's to parameters in a function, you do that in the decompilation window. You can build custom structures and assign them and build custom data type aliases, function types that work for function pointers that are being passed around. You can build all that using that box in the bottom left-hand corner of the main window. So let's zoom in on some decompilation, and specifically here, we see how Ghidra has automatically propagated the types for the nanosleep function to other parts of this function that uses nanosleep. So Ghidra knows about glibc. It knows that nanosleep takes 2 pointers to time spec structures, and so it's automatically kind of back-propagated to figure out where those things are assigned, and it's even filled in the function definition with the correct types up there for the data that's being passed in. So now you've got to commit this by right-clicking and clicking commit params returns, but after you commit it, Ghidra will propagate that information throughout the code as far as it can go. If you love the function graph function within IDA, then Ghidra also does function graphs. It's up under the window menu. Then, of course, there's a bunch of other cool features that we don't have time to talk about. Middle-clicking on entities to highlight them throughout your code is really handy. So I recommend trying that. And it's got undo, which is a really nice feature. It's in IDA now, too. But we came to talk about scripts and scripting. So under the window menu, there's the script manager. If you click on that, you'll get a whole list of scripts, and most of these are Java scripts. Not JavaScripts, but Java space scripts. And there, I mean, I'm not a huge fan of Java. It works pretty well, but they are great examples for how to use the Ghidra API to interact with all of your decompilation and disassembly. If you download and install my script, then it'll show up under the PCode category, and you just double-click on it to run it once you're in the function that you want to emulate. So let's talk about PCode emulation. First of all, why would you want to do this? It's kind of a middle ground between static and dynamic analysis. When you're doing static analysis, as you do in Ghidra, then perhaps you have a function and you want to investigate, if I provide these parameters, what kind of outputs do I get? Normally you could fire up a debugger and find this out, but if the function call is way down within the middle of the program, it might be really hard to do that bit of dynamic analysis. So this simplifies that, but also simplifies the case where the code is malicious, or the code is for an architecture you don't have an emulator or hardware for. Or maybe you've got the hardware, but how do you hook up a debugger on this microchip? It's pretty tough. So that's why you might want to use this software. And the demo code that we're going to do is relevant to this week. There's the NSA released a Python, Python version of an Enigma simulator. And so I ported that to C real quick and threw it into Ghidra for analysis. let's get that started because it takes a couple minutes to run. So I've got Ghidra running over here already. I've got a project and the Enigma code imported. The function that we want to analyze is called runalg. I wrote this myself to play to the strengths of my terrible code. But we'll pull up runalg over here, and it's already got the function signature up here. We'll talk about this more in just a second, but it takes 5 character pointers, so 5 pointers to strings as the arguments. And now we'll pull up the PCode emulation script, PCode interpreter, and we'll start it running. So the first thing it's going to do is ask for those parameters to pass in, and we're going to pass in, these are pointers that it needs, so we're going to pass in memory locations. It already knows what I've done before, so it's 0, 8, 16, 24, and 32. And it's going to start munching on that. It's got this awesome dragon. I love it. But we'll go back over here. So the specific parameters that it takes are listed there on the top in order. The first parameter is the output location for the encoded or decoded Enigma output. The next is the key, 3 letters, the starting positions for the Enigma rotors. We've got 3 rotors in this simulation. The next is the rotors that are selected. So I think there's about 8 rotors that we know about for Enigma. So we're going to use rotors 1, 2, and 3 in that order. Next are the plugboard swaps. Here we're just going to simplify and not put in any swaps. And then there's the input text. So just 7 A's. We'll see what we get out. In order to set up this state, those things have to be in memory so that we can pass their memory locations as the function parameters. So in the middle, we've got what the RAM is going to look like after we do the setup on the bottom. And then those 4 lines at the bottom set up those items in memory. So right now, unfortunately, I don't have a great interface for setting up the memory before you go in and execute some PCode as a function. But that's just, you can edit the Python code and put those lines in. And that's exactly what I did to set up memory initially. See, still crunching, should be almost done. Running, about 2¼ minutes later, you get the output. So the output is the return value from the function. That's normally what you want, but here, it's just an error code, right? So it's going to return 0. It's not going to have any errors during execution. But you also get as output of this Python script the state of the registers at the end and the state of the RAM at the end. So from that, at address 0, if we copy out the bytes, we can reconstruct the string from memory. And the letters that we get on the output are FTZ, MGIS. Oh, awesome. So this is finished over here. Output value is 0. We'll scroll up. We've got the registers listed with their names quite nicely. And then we've got the RAM as just an ugly dump right here. But you can see some of those same values, 46, 54, 5A, 4D. 46, 54, 5A, 4D. So it's output the same thing as before. Now the test is, does the original C code produce the same output? It's on a slide, so it's not much of a drum roll required. It does. So the PCode emulation produced the same result as the original binary, and that's exactly what we want to see. Let's talk about some shortcomings and limitations. The biggest one is that syscalls are part of the operating system where these binaries run. So when the PCode emulation is chugging along, it's adding, it's moving memory around, it hits a syscall, it doesn't have that OS code to execute it, to emulate, to do that syscall. So right now, they aren't handled hardly at all. The Anger framework has implemented some of those syscalls, so I'm hoping to kind of marry those two together and get some syscall emulation, but right now, it's not handled. The other main thing is right now the interface is really ugly. That's something that we can fix. Anyway, this is a personal project. This is not reflecting anything on my official work, but eventually I love doing this, so all that stuff will get fixed. Let's talk about Ghidra scripting with Python more broadly. Why would you want to do that? Well, the alternative is to use Java. And, and Python's got a ton of great stuff that's built into the standard library, and there's a ton of other projects out there on the internet that you can import and employ alongside your script. So those are some great reasons to use it. Ghidra uses Jython, which is a Java implementation of Python that hasn't been updated recently. So it's still back on 2.7.1. So that is a limitation if you try and use other people's Python code. In order to create a script for Ghidra in Python, you're just going to create a normal Python script. You can see this is just a totally stock Python script. At the bottom, there's even the if name equals main guard to prevent importation running this code elsewhere, and that works exactly the same when you run this script in Ghidra. So one recommendation I've got, if you're going to try and program, next we're going to talk quickly about the API in Ghidra, but there's a bunch of JavaDoc documentation under help, Ghidra API help, and it looks just like the JavaDoc documentation you're used to, but those functions work in Python as well. So Ghidra has some specific types, some objects, address, program, and language are some of those, and you can get instances of those by asking the user with these ask functions. It'll pop up a box on screen and the user can enter data. Also, if you want to introspect about the current program or the current selection that the user has made on the screen, get program and get address are globals that will give you the current binary that's open and information about it, and the current address selected on the screen. And then for your perusal later, if you're trying to use this, some documentation I haven't seen too clearly elsewhere. If you want to get information, what Ghidra knows about the program counter for this architecture, you can use this get program counter function, the endianness, the processor name, and register size. And then if you want to find information that Ghidra knows about the stack pointer on this architecture, and with this given compiler, the get stack pointer and some of these other functions are really useful then. So you don't have to pre-program information about some of these architectures. Ghidra knows them for you, and you can learn them at runtime. So we're just going to close with some links. Again, at KC0BFV is my Twitter handle. I posted a link to this if you want to get more info about the links. But just a shout to that second walkthrough. I was given at Infiltrate 2019, and it was kind of a great little Ghidra walkthrough at a medium level. And then at the bottom, I've listed where some of the Ghidra documentation is, both online and after you've unzipped Ghidra, where it's located. So I'd be happy to take questions after this. Are there any I can answer real quick right now? Shoot. So the question was, can you run Ghidra under Java 8? I haven't tried. It's not listed on their website as supported. They say you should use JDK 11, but OpenJDK works, and they actually recommend it, so that's really nice, I thought. Yeah, I'm sorry, I don't have a better answer for that. Any other questions? Awesome. Hey, thank you so much for your time. I hope you enjoy the rest of the con. Thanks for coming to my talk.